All right, we'll get started with our operation analytics this week. But before we get to the details of it, there are a few very simple mathematics you should be acquainted with. One of them is actually pretty simple and something you've always done, but let me formalize this a little bit so that we can use that. The idea is what we call expected monetary value. Well, monetary is kind of just for business purposes, but it's really the idea of expected value. And this is something you've always done. Let me start with something you have done. All of you have definitely done in the past, and build onto it. Suppose this is the syllabus you got in your class. You have 4 things that will contribute to your final grade. You have homeworks, you have quizzes, you have midterms, and final. Let me use a different color here. And your teacher told you that homework contributes 30% to your grade, quizzes 20%, midterm 25%, and final 25%. Okay, and I changed slightly a bit, which probably you wouldn't see in your syllabus. This is 30% is 0.3, 20% is 0.2, 25 is 0.25, and 25 is 0.25. One of the first things you must have noticed is all this add up to be 1. I'm not sure how much of you have noticed, but it always has to. This percentage have to add up to 100%. If that was not the case, suppose this only add to 80% or this adding up to 0.8, you could get 100% in all your assignments and still not get an A in the class, right? That's very important that all these probabilities have to add to 1. Okay, that's very important. Let's redo the calculation you guys have always done in the past. Suppose at the end of the semester you got 89% on your homework, 79% on quiz, 84% on the midterm, and you did really good on the final and you got 92% on the final. Well, the big question is, what's your final grade? Well, the normal process, what you would do is you would have a weight times grade. Okay, your grade. So the weight for your homework is 0.3 and you got 89. The weight for the quizzes is 0.2 and you got 79. 0.25 times 84, 0.25 times 92, right? And let's call this some sort of sub-score, if you will. This is really what the value is. 0.3 times 89 comes out to be 26.7. 0.2 times 79 comes out to be 15.8. 0.25 times 84 comes out to be 21. 0.25 times 92 comes out to be 23.0. You add this all up, you got 86.5, a solid B, right? So this is how you did it, right? Whatever you call it, this is at the heart of what we're going to do, the expected monetary value, the dreaded expected monetary value. Well, we'll formally define it in slides I'll post, but the idea of expected value really is, it's the mean of the random variable. It's really the mean of the random variable. A very important concept which people find it pretty interesting is this mean, this expected outcome, does not have to be one of the values in the random variable in the set you're considering. What I mean by that is this 86.5, what we're calling your expected value, or what's your the equivalent of expected monetary value. This expected value does not have to be one of the values. I mean, you never got 86.5. You got either 89, 79, 84, or 92. But your expected value is 86. That makes sense? So this value does not have to be one of these x's. Okay? This math is really at the heart of what we're going to do. Let me build into this. Before we go to look at the business example, let me show you one more example where you might have seen this before. Suppose you roll a die. You roll a die for thousands of times, and you get 2, you get 7, you get 6, you get 5, you get 3, and you do this for thousands of times. So 6, 4, 2, or something of the sort. And you want to know what was your expected number. If you roll a die, what is the expected number you would get? You might get 2, you might get 3, you might get 6, whatever, right? So that we can use the same kind of math. Supposing the die is fair, the probability of getting 1 is 1 by 6, 2 is 1 by 6, 3 is 1 by 6, and so forth, right? So events that can happen is you can get 1, you can get 2, you can get 3, you can get 4, you can get 5, you can get 6. Call this your axis, the random value. The random value could have been 1, random value could have been 2, and so forth. There's a probability associated with each of this random value. The 1 could have been, the probability of being 1 is 1 over 6th. The problem of 2 is 1 over, the probability of 2 is 1 over 6th, 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 and so forth. If you notice, all this will add up to be 1. Right? To find the expected value, all we gotta do is x times p over x. So 1 times 1 over 6 is 1 over 6. 2 times 1 over 6 is 2 over 6. 3 times 1 over 6 is 3 over 6. 4 over 6, 5 over 6, 6 over 6, or 1, right? If you add all this up, it will come out to be 21 over 6, which is same as 3.5. Again, the same idea. You never got 3.5, and when you roll a die, if you get 3.5, that would be pretty weird, right? There was no 3.5 there, but your expected value of rolling a die is 3.5, right? It's right at the middle of 3 options and right at the middle of other 3 options. Now, how does this fit into the business problems? What does it really mean? Let's do some practice problems. Let's do one practice problem for sure. All right. Okay, suppose, I can't make this bigger, can I? All right. So this radio station is giving away has a giveaway contest. Okay, when the person answers the right answer or whatever, they could either take $95, or they could I can figure this out to make it a little bigger, or they could either get to choose one of the 3 envelopes, which has either $500, $100, or $30. So what should this person do? Should this person take that $95 in cash, or should pick one of the envelopes? And this is something business will face all the time. Should we do this, or which we know for sure, or should we, or there is some probabilities of having this versus this? Should we change the prices, or things like it? This is usually solved with what we call a decision tree. This decision tree is exactly the same as what we have done before, the expected value idea. It's a little fancier. There are 2 kinds of nodes, and the first kind of node is what we call a decision node, because a company or the player or whatever that is, the interested party we are in makes a decision. That is represented by a rectangle or a square, right? This is what we call decision tree. A decision is actively made here. Decision node. The next kind is a circle or oval. This is an event node. Event happens. The player doesn't have a control. Somebody else might have a control, or it's just random. Okay, and then we have these lines to show the actual events. Actually events, and this is where we write the probability. Let's work an example, in exactly this example. Okay, so what is happening here? What's happening here is this person got selected, and he has to make a choice. I'm going to do this again. This person has been selected, and this person has to make the choice. Okay, so that's why this is an decision node. Exactly. So this person has a decision node to make cash or choose envelope, right? That's the decision this person has to make. Okay, the choice is presented to this person. Now we can do this by showing the 2 arrows, right? These are the events, right? These are the 2 events. Either choose cash or choose envelope. Now you have to notice there is no probability built into here, because it's the choice the person makes. There's no probability. There is no probability in choosing cash or envelope. It's his choice. Because it follows a decision node, there is no probability here. But if he chooses cash, there is 100% probability, that is 1, that the cash is $95. If he chooses envelope, 3 things could happen. with 1/3 probability, it could be $500. With another 1/3 probability, this could be $100. With another 1/3 probability, this could be $30. These probabilities are important. Remember, for this event, following one event node, following this event, all the probabilities will add up to be 1. Well, in this case, it's pretty simple because there is only one, right? Only one adds up to be 1. Following this event node, there are three actions, three events that could happen. If you notice, these 3 will add up to be 1. 1/3 plus 1/3 plus 1/3 equals to 1. That is a very important property. When you make a decision tree, that doesn't happen, you made a mistake. Now, we can use this setup to understand what decision should this person take. Remember, this person has this choice or this choice. It's his choice to make, right? Which one is the best choice? Well, this person could be risk averse and all those things, but for business case, what is more valuable? Okay, let's see, and this is what we call EMV, expected monetary value of choosing the cash, the first one, right? We are trying to decide what decision should he make here. Okay, he can either go this direction or this direction. The value of choosing this is, well, the expected value is, there is a probability of getting 95, the event is 95, and the probability, so they call it the X, the probability of the X is 1. So that is, he would get $95 the expected value is $95 if he followed this direction. Well, what happens if he followed this direction? EMV is EMV of choosing envelope is, well, X is 500, associated probability is 1/3 plus $100, associated probability is 1/3 plus $30, associated probability is 1/3. Okay, this is 1/3 of 500 is 166.67 plus 1/3 of 100 is 33.33. 1/3 of $30 is 10, coming out to be $210. Again, the same point I made earlier. There is no way he's gonna get $200 in any choices when you choose envelope. It's either gonna be 500, 100, or 30, right? It's never gonna be 210. But the expected value is 210. So a business person or anybody rational sitting here has a choice to make, either to choose this or to choose this direction. If he chooses this direction, his expected value is 95. If he chooses this direction, his expected value is 210. Which one should he choose? Well, duh, he gotta choose this choice of envelope. So this is really decision tree, and we're going to use this notion on a more complex setting, but the idea is exactly the same. You have only 3 symbols: a rectangle for a decision to be made by the player that you're drawing the diagram for. This is event node. This is it happens, in the sense there are probability involved in it. It could be done by somebody else, it could be the force of nature, whatever it is, but the person cannot control which of this is going to happen. There's a probability associated with it. All this probability will have to add up to 1. All this probability in this has to add up to 1, and so forth. And then we'll start from the back. For each event, we find the value. And we come back and we'll have this multiple layers of trees. But the notion is exactly the same. The value of choosing this decision is 95. The value of this decision is 210. So we choose the value that has the higher expected monetary value. That's all there is to EMV, and we'll look into more complex problem as we move along.